So we're talking about derivatives, and this is the typical way of how we find derivatives analytically in a precise form with a limit. So we build all this machinery of limits in order to be able to handle all kinds of limits, and one, the most important is, I suppose, is the derivative. So that's how it works out. As you can see in the middle, that's the challenging part of sometimes you have to work out the algebra in order to remove the indeterminate expression, turn it into a determinate expression. So 0 over 0 turns into something that is works out just fine because the function is continuous. Okay, so the trick is, this is one of the trick. Another trick is factoring. Another trick applying some formulas of multiplication or of trigonometry or something else. So all of these are challenging. I just don't want you to spend too much time doing that because it is purely computational, and it is unclear how much actually contributes to the understanding of the concepts. You just need to do this a few times in order to feel comfortable, and even though you might get stuck with a problem like that because there's a trick, and if you don't know the trick, you're pretty much in trouble. Okay, so that's an example. So just the hope is that, well, I'm certainly not gonna do anything of this kind excessively on the tests, but it certainly might come up in a simpler form. So the idea of how to resolve indeterminacy should be clear. It should be clear also what we're talking about, that fraction, the difference quotient, limit, and the meaning of the derivative. Okay, so that's the point of why we bother dealing with the derivative as a limit. Okay, and another one is problems that you encounter frequently is when the function is given by data. Okay, so we already did that with the spreadsheet, but you also might what was it? Limits of functions. Okay, so this. So where's the data? This is the data, and every step is computed by formula. But remember, we actually did initially computations of this kind with data given with numbers and written on a piece of paper, and we did it by hand. So that's another problem you should be able to handle, and that's compute the difference quotient from the data. So, and that could be any absolutely arbitrary numbers might be given to you, and then the question would be, what is the either average rate of change? These are also words that mean the same thing. So average rate of change, also average velocity, even though this one invokes physics, but then also difference quotient, and then finally the slope of the secant line. All of these mean exactly the same. Okay, so slope of the secant line, just remember the picture that we did yesterday, and just a geometric interpretation or visualization of the difference quotient. So either f of b minus f of a over b minus a. So that is average rate of change or difference quotient over the integral ab. So we're studying function over period integral ab, and then this is what it looks like. Pretty much rise over the run, right? And then you can plot the secant line as we have a f of a, b f of b, and we draw a straight line through these 2 points, and so this is the secant line. And where is the graph of the function itself? Well, we only have 2 points of it. That's it. So when you get to the limits, then you cannot stop here if you're looking for the derivative, because then you have to have this. You have to have the limit getting shorter and smaller and smaller. Okay, but this is what you might compute in the spreadsheet. As you can see, data goes vertically typically. You just assume the reason because you fit more. You fit more and more rows. They are narrow, but generally you might encounter functions very frequently in the form of two rows. So same thing. So I don't know, and then the numbers might be arbitrary, but I'll say 1, 1.2, 1.4, 1.6, 1.8, and then numbers to -5, 5.5, -1. Okay, so and then there's a right away you have a bunch of intervals, right? So one interval and then another interval like this. So each consecutive pair of consecutive numbers might serve in the x-axis might serve as the interval AB, and over that interval you will be computing all of these, well, the same thing. So for example, if I take this one, what is my difference quotient? It will be rise, which means that y, 2 minus 1 over the run, 1.2 minus 1. Okay, so it's 1 over 0.2, it's 5. Okay, so you don't even have to plot anything. There is no graph behind this function because all you have is the data. So think about it as if there's a sampled functions, just like those speed we read from the odometer. We read the speed to compute the velocity. Okay, and then you keep going, and the next one is what is it? -5 minus 2 over 1.4 minus 1.2, so it's -7. I'm sorry, -7 over 0.2, which is -35. Okay, so once again, another average rate of change. Okay, so let's take the green one. So this one over this interval. So what's the difference quotient? What's the rise?
Negative
Minus 5.
Right.
Yeah.
And over 0.2.
Yeah, it's the same thing. 1.6 minus 1.4. Yeah, it's 0.2. And then in here we have negative 0.5, which gives us a negative 2.5. Yeah. Thank you. Okay. So that is a simple problem. I mean, you can see there's a purely algebra here, and it's as if you're not studying calculus of continuous change and limits, but rather going to some previous course. But it is also something that you just have to do a couple of times to get comfortable with it. Another important skill, it is deriving the same conclusions in a manner almost similar to that from graphical information, from graphs of functions. So here I have a picture one of these. Yeah, okay. A function, as you can see on left, there is no formula and there is no data. So remember, we did it with formulas, we did it with with data, table of values. Now that's the third possibility, when you have nothing but the graph. Okay, so and you might be asked to find the derivative at various points of this graph. Okay, so all right, so that one red point is marked. It is it is marked on the x-axis because that's how usually the question is being asked. At time x equals -4, 1, 2, 3, 4, what is the rate of change of this function approximately? So what do? I first find the point that I care about. This is, I go vertical and I find that this is the point that I care about. Okay, and then what do I do?
Figure out the y value of it, and then you put it in a table.
Well, I will figure out the y value will be this 1.4 or something like that. So how does that help? Well, the trouble with this is that you don't want to do secant line. I mean, even though it makes perfect sense to approximate, we do approximate the tangent line with a secant line, but that is when we have many values, and we can pick and we can make it better and better. At this point, it wouldn't make sense if I picked a point. So it is possible I could pick a point here and draw a secant line from these 2 points. It will be an approximation, but I could do a better job if I just try to draw a line that is as close to the tangent line as possible, in the sense that, with the curve, the straight line that touches the graph. Okay, so I take some, what do I do? I pretty much take a straight edge, okay, okay, and I try to put it on, well, you can see it, okay, actually there is a way to do it like this. I take a line, and how about, what color do I like? Let's take green, okay, and I draw a line like this. So suppose I missed it, that doesn't matter whatsoever. Okay, so now I'm trying to fit it into the graph around the orange point, not the red point, not naturally, but the orange point, as closely as possible, so that it resembles, well, coincidentally it's pretty good. But I could do better. Why? Because it actually it is close, right, but it's closer. It has to be evenly distributed. So as you can see, on the left it stays with the curve for a while, and on the right it leaves it. So it appears to me that I'd rather have a slightly increase of the slope like this. It's slightly better. Does it look reasonable? Okay, so that's a tangent line. It is perfectly reasonable. At this point, I could either leave it here, or I could actually, because what I'm supposed to do with that curve is this. I actually need it to be, I need to remember I need its slope. To have a slope, I need a rise and the run, so I could just as well, and take it here for my own convenience. So I know I don't need the exact location of the tangent line. I need its slope. So I'll locate it in such a manner that I can figure out the slope quickly. What's the slope? 5 divided by 3. That's right. Yeah, that's right. 5 is the, come on, shit. 5 and, oh, that's so thin. 5 and 3. So slope of the green one, 5/3. So I go back, and that part that I picked, well, let's make it green, 5/3. The slope is 5/3. So the derivative is at that location is roughly 5.3. I could write it f prime. So if this is y equal f of x, this one is y equal f of x, then the information that I have derived is f prime of -4 is equal to 5/3. Okay? So, and then you should be able to do that same thing more of. So, for example, let me pick 0 as the point. So, suppose the value of x I care about is at 0. Once again, I go. Let me pick this time blue. Okay, so I go up. I find the point where my point is located. It's pretty thick, as it probably could be thinner, the graph of the function, so we can do a better job. But it's okay. So that's the point we're looking at. Once again, I draw a tangent line. Once again, I draw a line like this. Oops, that's not a line. Line. Okay, line, straight line. Okay, now I try to see that it fits. It's not. Which way should I turn? Left, clockwise or counterclockwise?
Counterclockwise.
Like this? Okay, so maybe. I thought for some reason, let me see. I don't like, so this is the point, I don't like the, oh, well, let me try to go the other way. No, that's this way. How about I go, well, doesn't really matter. They're all pretty good, okay, unless the curve is thinner, which I might try next. The curve is thinner, I could try to, I just go ahead and use that. Okay, so that's acceptable. Okay, so I shift it here once again, put it in the convenient location. Okay, so what's the answer? So we need the slope again of this line. What's the slope?
Be about 2, I don't know, 2 and then negative 2 and something.
No, which one's which? So what's the how you do it? You don't try pick one point. All you need for the slope is one point, because the second point is already found. It is the origin. Okay, so all you need to pick is one point. You pick the one that is closest to one of those crossings. Okay, so I think this is pretty reasonable. So I pick that point, and then I just look at the y and the x. Right, that's all. So what do I get? So the rise is negative 6, and the run 4. Okay, so it's negative 3/2. So once again, how would I describe it? I write directly f prime of what was the 0 is negative 3/2. Okay, so and then you'll get to used to this, and you will be doing it easily by examination. At least you have to be, as we have noticed, the difference between these two is one is positive, the other one is negative, right? That's the slopes that you may have seen in like pre-calculus class, right? And so negative, positive, positive, negative, steeper, more negative, or steeper, more positive, and 0. Okay, so these things you should be able to see from the graph. So for example, without doing any other computations, we have 5/3 there, and we have 3/2, negative 3/2 there, negative 3/2 there. So for example, if I move to say this point, what do you think the graph is without any plotting? Roughly.
The slope?
Yes, the slope.
From that point, it's probably negative a little bit at first because it's going to the...
No, I'm talking about the tangent line at this brown point. So in comparison, compare it to the previous point. What has happened to the slope? I think the tangent line, did it rotate clockwise or counterclockwise?
It's not nearly as steep.
It's not nearly as steep, so if it is negative 3/2 there, so what do you think this one is?
It's probably negative 1/2.
Negative 1/2, or I'm looking at it, looks like 45 degrees.
Yeah.
Which is, does look a lot, so then it's negative, then what is the value if it's 45 degrees? 45 degrees down, negative 1.
Negative 1.
Right. Okay, so similarly, and then you can just doing that thing as many times as necessary. This point, what's the slope? Well, if in any doubt, just draw a line. Okay. It is 0, right? So this one is clearly 0. Slope is 0, and so on, and then we could ask ourselves what is happening. We already the Excel did that for us once. Every point it computes pretty much the same thing and tells us to build the whole function, but we have to do it just looking at the graph, and we should be able to tell what's happening to the slopes. So as you can see, it starts very steep, and I don't know, it could be as high as, I don't know, 8, okay, and then it goes down, maybe 6, 4, this is 5/3, 0 again, then it becomes negative, right? So maybe -1, -3/2 here, -1 again, 0, starts to grow, becomes 1. Here it might be 2, and it starts to decline, so 1.5, 1 maybe, and then 0.5. Reasonable, right? So you just see how the slope changes, and it changes. Imagine as if you have a bunch of lines, but then you can sort of bring them together in one place and see if there's how they rotate with respect to each other. So I have only 2 here, but you can imagine that between these 2 points, the green one and the blue one, there are a bunch of other tangent lines like this. Every point has a tangent line, okay, and every one has a slope, and if you bring them together, you will see that there is a change of that slope, maybe in that manner. That's what has happened. So instead of having one slope at a time, we have a bunch of them. So that's pretty much how you build a new function called the derivative function of our original function. So, but this time just the ability to quickly evaluate derivatives from pictures is important. Keep in mind, however, that it's very easy to get lost in this, especially if you look at Excel work. The trouble with Excel, well, you see the trouble with Excel if I try to evaluate a look at location. If I try to evaluate in the same manner, let me just take. Why is it not working? Is it working? Something isn't happened here. What happened? Okay, this works. This works. Something happened to the mouse apparently. So it moves, but nothing else. So if I do copy and paint and paste. Okay, let's try again. So I want to copy this, and I do push copy, and then it's supposed to paste here. It doesn't paste. Okay, paste here. Okay, so the problem is that is to watch out for. I could try. It looks the same as the problem we just solved, so I could proceed in the same fashion and say pick a point and draw a straight line over here. Well, maybe it's you can get pretty accurate here. So making sure that if you can make it thinner, and then you can make sure that there is a real merging going on. So you see merging, right? And either you move it away or not. You can the appearance, from the appearance, it seems that the slope might be 2 or something like that. But in reality, you would have to establish what it is. You have to look at the actual numbers, and your intuition might fool you because the Excel frequently is not to scale. So it's stretched vertically and horizontally, as you can see. These are supposed to be all squares, but they aren't. So this one is not a square. Well, I can assure you. You can see that this is not a square. Okay, so it is very frequently stretched. Same applies any kind of pictures that are presented in books and in scientific books. So the scale might not be there. But if you do it with if you look at actual numbers, you won't make that mistake if you look at the triangle, build the triangle right here. So don't go anywhere, but just plot the triangle in here. So this is the triangle. This is the triangle based on my tangent line. So however short or long my tangent line is used as the hypotenuse of a right triangle. Okay, and that if you do that, you'll get your rise and you'll get your run. So this is the run, and it is roughly equal to looking at the numbers on the left. It is roughly, what is it, 7,000? So from here to there.
Yeah.
7 or even more, right? So 7, maybe even 7.5, but let's say 7,000. Okay, and the number, the run is this, and this one is 2,000. So then the answer is 7 halves, 3.5. Because it's stretched horizontally, the slope is, it does not like 3.5, but as you can see, because it's stretched horizontally, the numbers actually are different. So make sure that it is, before you making quick estimates, make sure that it is to scale. As you can see, this one is to scale to begin with. X and Y have the same units. But even if they weren't, moving them carefully to the exact same axes as on the right gives us the correct computations, because we are using the right units horizontally and vertically, and we adjust for that for possible in disproportionality. Okay, so let's not delay this for too long, but we could also construct a function from its derivative. Okay, so if we know all these slopes, we can make a function. So this is how it might work. So if I have, say, my slopes are slopes might be say 1, 0, -1, -2, -2, 0. Okay, suppose these are my slopes, and so these are the slopes, and the value of these are the values of y then, and the value of x might be something simple, say 0, 1, 2, x, and this is slope 2, 3, 4, and 5. Okay, so I can combine these slopes of f, and then the question is find f. Okay, so the question is the same as finding the location from the velocity. So velocity is the difference quotient, and we did, that's what we did over here. But we'll see later how you can reconstruct backwards from velocity location, or starting with it from acceleration velocity from velocity location. But let's do it by hand first. So let's see here. Let me plot these. So slope 1. Okay, slope 0. Okay, slope -1. Slope -2. Oh, let me change the color here. Slope -2. Another slope -2. And then slope 0. Okay, so I just take them and assemble them one by one. Now let me copy. So I'm building them. Okay, and then okay, so I'll take these and assemble them like this. So I take them one by one and just move them like this. Okay, this doesn't fit. Move it. Okay. So you can imagine that if we had more slopes, more points, smaller intervals, that graph at the bottom would be actually a continuous curve. Okay. But generally we can reassemble things either by hand, by hand meaning by just moving stuff around, or numerically, which is what Excel will be doing, and that's how you solve very complex physics problems. In fact, well, let me show you this one. This that recently, similar to what I showed you on the first day, but this one. Okay, you're gonna open it. Not this one, no. Once again, so that's not the one I clicked. I clicked this one. Okay. It's called the two-body problem, which is pretty much nothing but a motion. Okay, so I have to go and change the settings again. So this one has circular settings, and it has to be changed early on. Otherwise, it just will be. Okay, so allowed 9 up. Okay, so it's the same thing. Same thing, it is two-body problem, so instead of, unlike the solar system, when the sun is so big that you can assume that it is unaffected by the gravitation of the Earth, here there are two bodies that are comparable size. One is 500, the other is 300. So then I can rotate them, and then it will be recomputing. Okay, what's the problem? What is the problem now? I don't think it understood. I didn't mark this one. Okay, so let's try again. So 9. Yeah, see? So it is recomputing the stuff, and you have a possible motion of two comparable sized bodies, and it is done in entirely the way that I just showed you with those pictures, how if you know the slopes, if you know the acceleration, you can find the velocity. If you know the velocity, you can find the location. So this is the location, but initially what we are given nothing is but the forces between the two bodies. And the forces between the two bodies give you the acceleration according to Newton, and then you get the velocity and then acceleration, and nothing else is required. You don't need two limits or anything of that nature. As you can see, that's pretty good idea of what is going on. You can see also you see that little cross over there. You see that next to the x-axis, right there, just passing it. You see it? Not a cross. It's some kind of little star. So that's the center of mass of the two objects, and they are rotating around it. Okay, so if you put the center of mass at the center, then you can see that the objects are actually following pretty much elliptic orbits. So the point is, more complicated process than what you encounter in your projects, but technically there is nothing more than a few lines of very short lines of formulas that you have to write, because the formulas are right here. These are the formulas. This is the law of gravity that we talked about. Remember, so the force between the two objects is proportional to the mass, and it is proportional to the square of the inversely proportional to the distance between them, the square of the distance between them. Okay, so but this is where you start. This is how you reassemble the function from its derivative. Okay, so this is what we have talked about. So this is an exact computation, so which is not very practical for modeling, but my definition. It's still average. So the average is the difference quotient is this, and then if we take the limit of the difference quotient, that is called the derivative. I just can't find where I put it. I guess I'll have to write up again. Okay, so I'm positive I wrote it. So limit f prime of a is limit h goes to 0, f of x plus h minus f of x, f of a over h. So the derivative of y equal f of x at x equal a. The second formula is the same. We just used a slightly different way to do it. F of x minus f of a over x minus a. This one is slightly different because, slightly better, sometimes it's just better because you can actually see the difference quotient, you can see the change of x, you can see the change of y, and then you have the ratio. It is also sometimes better computationally, even though the example that we just saw was actually, or that one x squared, it's like 1 plus h squared minus 1 squared over h, and we worked it out through algebra and removed the indeterminacy. If you go with the second formula for f of x equal x squared at 1, it will be not as easy. It will be x squared minus 1 squared over x minus 1. Okay, so once again, if you use the first definition, you have this, and if you use the second definition, you have that. Okay, so what I meant is this. So from the first definition, that's what we did yesterday, right? So we have 1 plus h minus 1 squared. We expanded, remember that, and then we ended up with 2. Okay, so that's what we did, but we could have used the second definition, and then the difference quotient has a different form, and but it still has 0 over 0 indeterminacy. Remember, x goes to a, so we are looking for a limit of this thing with x going to 1. This one's limit with h going to 0, so that's kind of simpler. Indeterminate expression 0 over 0. Okay, so what do we do? Just for practice, what do we do with the second expression? How do we evaluate the limit?
You negative quadratic on top.
Negative what?
Obviously, and like, how do you find the limit of that?
Yeah.
You break apart x squared minus 1.
Right. And so what? Yeah. So what do I get?
X plus 1 and x minus 1.
That's right. And I cancel. And just the same idea. It's the same thing is hidden. And the answer is 2. Once again, the magic word is x plus 1 is continuous. Why does it work out? Because x plus 1 is continuous. Okay, so that's a function when the derivative as a limit computed as a single limit at every point of the at a given point of x, as many points as necessary. Okay. So some might look more complicated than that, but you always end up with 0 over 0. Always have to do algebraic trickery sometimes in order to resolve the indeterminacy. Here's another example. F of x is equal to 1 over x. Okay, so once again at a equal 1. I'll take the second definition again. So the limit. X goes to 1, okay, it will be simply 1 over x minus 1 over 1 over x minus 1, right? So the function is 1 over x, the value, specific value of x is a equal 1, so I'm using the formula at the top, right? So 1 over x over 1 minus 1 divided by x minus 1, 0 over 0, you're going to see that every time happening. So you never apply the difference quotient, you move on to algebra. And what algebra do we do here? There aren't too many things that we can do. No, don't jump to the answer. What is the, how do you resolve the indeterminate expression? The answer is always the same. It is the algebra or trigonometry or whatever, but it's pretty much the same. The word algebra covers everything. but the question is what is exactly do we do?
Would you multiply the top, the numerator and denominator by x?
Well, I suppose you can say that, but it's like we're doing common denominators. So you have to do something with the numerator in order then to have a hope to cancel the denominator. And what do? Oh, well, you do common denominators. One denominator is x, the other is 1. So indeed, I multiply both by x. So 1 over x minus x over x minus 1, right? And then now I have common denominators, so I have then 1 minus x over x, and the whole thing divided by x minus 1. Okay, now I can simplify, right? So what do I get? It is 1 minus x over x divided by x minus 1. Okay, so what do I get?
With the x underneath of the x minus, or 1 minus x, and the x, and the bottom x, and the furthest denominator cancel would be 1, so it'd be negative 1 on the bottom.
No. How do you can cancel? You can divide, but that does not resolve the indeterminates here. Remember, if you are trying to figure out which way to do simplifications, point out where the problems lie. Where are the zeros? So when x is equal to 1, what turns into 0? All of these. These are bad. Well, I put them in green for some reason. Well, let's put them in red to make a point that it is bad. So this is bad, that is bad, bad, bad. Okay? So if they are bad, that they are the one that have to be removed, and it is, in other words, somehow cancel them. And what's the relation between 1 minus x and x minus 1? One minus x, x minus 1?
Are they inverses?
Not inverses, no. 1 minus x, x minus 1. Say this is 1 and this is x. So x minus 1 is this, and 1 minus x is that. So minus x, x minus 1.
Oh, the answer will be negative of that.
Yeah, negative, right? Yeah. So it does come up. It sometimes look very different, and then, well, it's pretty much the same thing. And certainly when you want to cancel it, you can cancel it. So, and then the only extra negative sign is the only thing that negative 1 is what's left after the cancellation. So I can cancel this, and I just will be left with negative 1. Right. So those two bad guys are gone. They were not exactly the same, but well, if you tweak it a little, you realize that they're pretty much the same. And then the indeterminacy is gone because we're not looking at x equals 0. We're looking at x equals 1. So we just plug in and we have negative 1. And once again, the magic words are because 1 over x is continuous, and this time I want to be more specific at x equals 1. Okay, because it is not continuous at 0, but as a rational function, other than at 0, elsewhere it is continuous. So the slope is negative 1. You can confirm that easily with the graph. This is the slope like this. Okay. So I guess there's another one. So back from algebra, if we look at geometry one more time, another way to solve this problem is so finding the tangent, the slopes of the tangent lines by examining the graph is to what we try to use that I said you zoom in on the graph, but this time you can instead, how about we blow up instead? So that's once again this kind of this paint, right? This kind of software allows you to do a lot of things, and with zooming in is really not a possibility. More like the possibility is you can blow up. So I pick this piece, say I'm interested in, and then I'll blow it up. Okay, so I cut such a small piece that it looks almost like a straight line, but to actually determine the slope, it is more convenient if it is large. Okay, so I'll blow out by 300%. So resize 300%. Okay, well, it looks a little bit well, there's no good place to put it. Okay, well, okay, so let's just do our best and try to figure out it. Okay, I'm almost out of time. So if I draw a line here, that should give me the slope as well, and it roughly, so what is it?
About 3.
Almost exactly 3. So that's another way. Zooming in by blowing up. Okay. All right, so today's Wednesday, right? So we're done then.